everything you think you know about the Big Bang is wrong. And I'm not talking about conspiracy theories here. I'm talking about what physicists actually believe versus what they taught us in school. Because here's something that will blow your mind. Most physicists today don't believe the Big Bang was the beginning of the universe. Think about it for a minute. The Big Bang wasn't the beginning. So what was it? What actually collided? Was it a singularity or nothing or something else entirely? Stick with me, because by the end of this article, you'll understand something that even most science teachers get completely wrong. Before we get to the essence of the Big Bang, we have to go back to when humans first looked up at the sky and wondered, where did the universe begin? The Greeks believed the universe was infinite, while the Hindus saw it as an endless cycle of creation and destruction. In 1687, Newton turned all that thinking upside down when he published Principia, demonstrating that the laws of motion on Earth applied to the entire universe, and that gravity was the basis of all interactions. But Newton himself was stuck in his own paradox. If gravity pulls everything together, why doesn't the universe collapse? He was forced to believe in a static, infinite, perfectly balanced universe. This belief lasted for more than 200 years, until the question, why is the night sky dark, appeared and created the first cracks. If the universe was infinite, the light from countless stars should make the sky bright. The darkness became evidence against Newton's own model and suggested that the universe might be much more dynamic than people thought. At the beginning of the 20th century, Albert Einstein appeared and changed everything again. In 1915, his general theory of relativity proved that space and time constitute space-time, and gravity is the bending of that fabric. By the 1919 solar eclipse, the prediction that light bends around the sun was confirmed, instantly making Einstein a global scientific icon and forcing the world to admit that Newton has been overthrown. However, Einstein's equations revealed what he did not want to face. The universe cannot stand still. It must expand or contract. Refusing to accept this idea, he added a cosmological constant to the equation to keep the universe static. He later called it the biggest mistake of his life. But modern physicists are skeptical. Was Einstein really wrong? Or had he accidentally touched on a deeper truth that the era could not understand? While Einstein was still struggling with the equations that bent space-time, astronomers suddenly faced a discovery that was enough to rewrite all of cosmology. For centuries, people saw faint streaks of light called nebulae and wondered if they belonged to the Milky Way or something else. Using distance measurements invented by Henrietta Swan Leavitt, Edwin Hubble determined that the Andromeda Nebula was about 900, 000 light years away, far exceeding the size of our own galaxy. In just one measurement, the universe had ballooned to millions of times larger than humanity had ever imagined. Those fuzzy clouds turned out to be full-fledged galaxies containing hundreds of billions of stars. Hubble continued to observe and discovered something even more shocking. Most of the galaxies were rushing away from us. And the farther away the galaxy, the faster it was moving away. This was exactly the sign of an expanding universe that Einstein's equations had predicted, but he dared not accept. The static universe collapsed in an instant. The revised Einstein equations now became prophetic. The universe was not stationary, it is expanding, growing as if concealing a primordial secret that we are only beginning to discover. Imagine rewinding time in an expanding universe. Galaxies are closing in, density and temperature are soaring until all matter, energy, and space are compressed into an extremely dense state. Georges Lemaitre called this moment the primordial atom, likening the present universe to the remnants of a cosmic fireworks display. if space and time are one, then this is not just the birth of space, but also the beginning of a day without yesterday. This is also the familiar textbook version of the Big Bang, an infinite singularity where the laws of physics break down. Hawking and Penrose have shown that this singularity is inevitable. But what few people talk about this model is almost certainly wrong. Modern research suggests that the singularity may be a limit of mathematics, not of nature. And this discovery opens a story far stranger and more fascinating than the one we're about to embark on. But before we go any further, we need to understand what actually happened in the very first moments after the Big Bang. Physicists have discovered that in the first moments after the Big Bang, the universe was so hot that it acted as a giant nuclear reactor, where protons and neutrons collided to create the first nuclei of hydrogen and helium. Theoretical calculations predict that the early universe would have been about 75% hydrogen and 25% helium. When astronomers measured the chemical composition of the universe, the results matched almost perfectly, as if the equations spoke directly to reality. However, the story doesn't end there. About 380,000 years after the Big Bang, a pivotal moment occurred. The universe cooled enough for electrons to cling to nuclei, forming the first atoms. And that magical moment changed everything. The light, trapped in the sea of hot plasma, was freed and began to fly freely through the universe. From that moment on, it never stopped. If humanity could find that ancient light today, we would have the oldest photograph of the universe, a direct trace of the Big Bang. The search for that early trace became one of the greatest scientific journeys of the century. In the 1960 seconds, while engineers at Bell Labs were testing a new radio antenna, they caught a mysterious background hiss in the data. They checked the equipment, tried every way to remove the noise, even climbed up to clean pigeon droppings to make sure no source of interference had been missed. But the hiss was still there, stubborn and inexplicable. And then they realized what they were seeing. It was the cosmic microwave background. Ancient light emitted 8 billion years ago, stretched into microwaves as the universe expanded and cooled. A signal from the very beginning of all. The discovery instantly became the jewel in the Big Bang Theory's crown and earned them the prestigious Nobel Prize. Humanity had finally heard the echoes of the very birth of the universe. But just when all the evidence seemed to be conclusively supporting the Big Bang model, the whole picture began to crumble. Three major problems emerged, three paradoxes that shook the foundations of what we thought was a complete story. And this is where we get closer to what really happened at the dawn of the universe. The first problem is the horizon problem. When scientists mapped the cosmic background radiation, they found something incredible. Its temperature was almost perfectly uniform across the entire sky at 7 Kelvin in every direction. This is an absurd uniformity. Even if light were to travel the fastest in the universe, two regions at opposite ends of the sky would not have had enough time to exchange information or equalize their temperatures in just 380,000 years after the Big Bang. It would have taken trillions of years to achieve that uniformity. So what makes the entire young universe so strangely homogeneous? The second problem is the flatness of space. Space can be flat or curved inwards or outwards. But our universe is, by measurement, perfectly flat, almost improbably. And here's the creepy part. A flat, expanding universe is incredibly unstable, like trying to balance a pencil on its own tip. If it gets the slightest bit off, it will topple over, leading to one of two tragedies. The universe collapses or expands too much and tears apart in its early days. Yet for this universe, everything is incredibly perfect, as if someone tuned it to absolute precision from the start. The third problem is the problem of magnetic monopoles. Given the enormous energy levels in the early universe, particle physics predicts that a whole host of magnetic monopoles should have appeared. They are magnets with only one pole, north or south, with no opposite pole. But what's the problem? In decades of searching, we've never found a single magnetic monopole. Not a single one. And if these particles did exist in the large numbers predicted by theory, they would be so massive they would stop the expansion of the universe in its earliest moments. But that's not what happened. And on top of all that, trouble is the singularity itself. Most physicists feel there's something wrong with the idea that the universe began from an infinite point where all the laws of physics are meaningless. Einstein even called the concept repulsive. The equations seem to lead us to something that can't exist, as if the universe is hiding something behind a mathematical veil, luring us down a blind alley that forces us to ask, did we get it right all along? And it is from these paradoxes that a surprising solution emerges, opening the next chapter of cosmological inquiry. This is where the brilliant physicist Alan Guth came along, and what he discovered completely changed everything we thought we knew about the Big Bang. Guth started not with the vastness of the universe, but with a much more familiar phenomenon, phase transitions. We know that water can go from ice to liquid, from liquid to vapor. But there are other more exotic types of phase transitions in physics. For example, pure water can be cooled below freezing and still not crystallize into ice. This phenomenon is called supercooling, a state in which the phase transition is delayed even though the conditions are right. Guth began to wonder if the early universe might have undergone a similar kind of delayed phase transition. And when he did his calculations, a result came up that stopped him in his tracks because it was too bold and too consistent to be a coincidence. If empty space really does contain energy, as quantum mechanics predicts, and if this energy is capable of accelerating expansion, then the universe would have expanded not just rapidly, but so rapidly that it is beyond all reasonable thinking. According to Guth's model, in less than a trillionth of a second, the universe could have expanded by at least 100 trillion times. An expansion rate that is almost unimaginable, but one that explains the paradoxes that have puzzled scientists for decades. Guth calls this period of hyperacceleration inflation. With that discovery, the door to a completely new picture of the origin of the universe was opened, challenging the entire way we view the Big Bang and moving the story into a much more interesting chapter. And here is the magic moment. Alan Guth's proposed hyper-rapid inflation neatly solves all three problems that have shaken the foundations of the Big Bang model. The flatness problem is solved first. Whatever the initial curvature of the universe, the extremely rapid expansion of inflation flattens it out like a balloon. The more the surface swells, the less the curvature, moving closer to perfect flatness. This is not a coincidence, but a necessary consequence of such a tremendous expansion. The horizon problem is also completely solved. Regions of the sky that today seem too far apart to ever exchange information were actually close together before inflation. When they were so close together, they had time to reach a common temperature. Inflation simply spread those uniform regions out across the universe, creating the temperature uniformity we see in the background radiation. The monopole problem also vanishes. in the supercooled state before inflation began, the monopoles predicted by theory could not form. The universe expanded so rapidly that all the conditions necessary to create these exotic particles were completely destroyed. But inflation didn't just resolve the paradoxes, it also revealed a deeper truth about the origin of all structure in the universe. Remember those tiny variations in the cosmic microwave background, those slightly different hot and cold spots that scientists have observed. Inflation explains the origin of these ripples. During the massive expansion of the universe, quantum fluctuations in the inflationary field were stretched and frozen into permanent ripples on the fabric of space. These were the seeds of everything. Over billions of years, gravity caused more matter to condense in those slightly denser regions from tiny quantum fluctuations. Giant galaxies were formed, which led to the birth of stars, planets, and eventually life. Without those quantum fluctuations, our universe would be a smooth, structureless sea of matter, with no galaxies, no stars, no planets, no you, and no me. So we can finally return to the original question, what was it that hit the Big Bang? The answer, as we'll see, is far from the usual picture. Let's start with a primitive universe that was nothing but empty space. No matter, no light, no particles, no atoms, not even heat. But empty here is not empty in the true sense. Beneath that shell of nothingness is a fundamental quantum field, the inflationary field, which carries with it an enormous amount of vacuum energy. It is this field that causes space to begin expanding at an extraordinary rate. A region of space the size of a grain of rice can swell to a size larger than the entire observable universe today in less than a trillionth of a second. The key point is, in that period, no matter had yet formed. Only empty space was expanding. Then came the decisive moment. Inflation ended, and instantly, in a cosmic blink of an eye, all the energy of the inflationary field was converted into matter and radiation. It was this violent conversion that we call the hot, dense Big Bang in textbooks. The cosmic microwave background radiation, the early nuclear reactors that created hydrogen and helium, all the properties of the young universe are all remnants of the vacuum energy released in that instant. This leads to a shocking conclusion. The Big Bang was not the beginning of the universe. It was not the moment when everything exploded from nothing. Instead, the Big Bang was a cosmic phase transition event, the moment when inflation ended and all the energy of empty space was converted into matter, light, and everything we see today. There was no collision. There was no singularity that forced the laws of physics to break down. There was just one primordial energy field expanding. And then at that fateful moment, boom, the universe as we know it officially appeared. But here's the really mind-blowing part. Inflation didn't end all at once. It didn't turn off like a switch, but rather in regions, in patches, in bubbles of space. That means that while inflation stopped in the region where our universe formed, allowing energy to be converted into matter and light, elsewhere inflation continued to expand, and so it did, creating countless other bubbles, each one giving rise to its own Big Bang, its own universe with its own physical constants, its own rules, and perhaps stories entirely different from our own. That's the birth of the multiverse, and we're simply living in one of those countless bubbles, a tiny sample in an endless, ever-growing field of universes. What's remarkable is that this isn't a fringe idea or a science fiction hypothesis. This is the most widely accepted view in the modern physics community, based on decades of calculations, models, and observational evidence, but it's clearly not what you were taught in school. Not long ago, even in mainstream science, it was widely assumed that inflation followed the Big Bang, that the universe began from an infinite singularity, and that there was no room for the concept of a multiverse. But science doesn't stand still. As new data emerges, old theories give way. As models that explain more phenomena emerge, we are forced to update our story. And today, the inflationary Big Bang model is the best, most convincing picture we have of how the universe began. Not from a singularity, but from an expanding field of energy, spawning countless universes like bubbles in an infinite sea of space. Some physicists think inflation is too flexible to be tested. The multiverse makes many scientists uncomfortable because we may never be able to test it directly. But here's what we know for sure. The hot, dense Big Bang definitely happened. Everything in the universe was incredibly close together and much hotter than it is now. We can actually see the evidence in the cosmic microwave background radiation. That's not up for debate. What caused that hot, dense state? What happened before inflation? Those are questions that are still being explored. Alan Guth himself said the Big Bang theory was never really a theory of the bang. It doesn't say anything about what went bang, why it went bang, or what happened before it went bang. And that is where we stand today, standing at the edge of the unknown, looking back at the moment our universe was born, knowing more than ever, but still pursuing the deeper mysteries of what started it all. So the next time someone tells you that the Big Bang was the beginning of everything, you'll understand better. You'll know that the bang wasn't the beginning. It was a transformation, a moment when empty space filled with vacuum energy became all we see, touch, and create. And that somehow, that's even more amazing than any singularity. Hey, don't stop there. The universe is full of secrets waiting to be discovered. Subscribe and join us as we explore more amazing mysteries of the universe, from black holes to the very ends of reality.